In this video lecture, we're going to talk about one-dimensional steady-state conduction, and we won't get clear through chapter 3, so we're just going to focus on one-dimensional steady-state conduction in Cartesian coordinates, where we're typically just talking about the x direction, so heat flux in the x direction. So to do conduction analysis, you want to start out with the heat equation, and if you'll recall from previous lectures, the heat equation is derived from doing an energy balance on a very small control volume and then shrinking down the dimensions of that control volume until you get a partial differential equation over which you can solve to get a temperature distribution. So by solving the heat equation, you can get a temperature distribution, and once you have a temperature distribution, you can apply Fourier's law and get heat flux at specified coordinates within your system. So the simplest case is one-dimensional steady-state conduction when you have no thermal energy generation. And again, I mentioned we'll be focusing on Cartesian coordinates in this lecture, which is the plane wall. But one-dimensional conduction could also apply to a tube wall, where you're dealing with a cylindrical coordinate system, or a spherical shell when you're dealing obviously with a spherical coordinate system. So you want to start out with the heat equation. So for the plane wall system, we're dealing with conduction only in the x direction. We're assuming that the y direction and the z direction in and out of the screen would have no temperature variation, so therefore there's no reason to try and characterize how temperature changes, because it doesn't change for these systems. So some of the implications are that heat flux is independent of x, of the spatial coordinate. And also, because heat flux is independent and because the cross-sectional area doesn't change in a planar system, that the heat rate also would be independent of x. And we discussed in previous lectures that when you're dealing with the heat equation, you need to deal with boundary conditions. So in the simplest case, you have these surface temperature boundary conditions, TS1 and TS2. So let's try and make sense of all of this. So if we have a particular system like this and we know the surface temperatures and we know something about the conductivity of the wall, we would start here with the heat equation. So this is the full heat equation in Cartesian coordinates. But you remember, we're dealing with a special case of the heat equation. So we're not dealing with generation, so we can get rid of that term. We're doing a steady state analysis, so we don't care how it's changing over time. And we're also assuming constant temperature in the we're assuming constant temperature in the y and the z direction, so that makes these derivatives equal to 0, so we can get rid of those entire terms. So what we're left with is this very simplified version of the heat equation. And this is actually quite a simple equation, and it's very easy to solve analytically, so you would just do something like this. You would take this equation and you can multiply each side by dx, so you get the derivative of conductivity times the first derivative of temperature with respect to x is equal to 0 times dx. We just move the dx over to the right-hand side from the left-hand side. By multiplying both sides by dx, excuse me. So then if we were to integrate both sides, we would get the conductivity times dt dx is equal to just a constant of integration. Let's call that C1. So one thing we can do now is just divide both sides by k, and that goes away from this side. And because k, we're assuming that k is independent of temperature in this case, we can just lump in k into a constant. So we'll just call this whole thing, I'm being bad with my nomenclature here, but we'll just call that whole thing C1. So now we have dt by dx is equal to a constant of integration. If we are to separate variables again, we get dt is equal to C1 times dx. And if we integrate, now we get temperature is equal to C1 times x plus C2. So remember, we had two boundary conditions, we're going to use. This is a second order differential equation, so we need to have two boundary conditions to specify these two constants of integration. And what you see when you have this particular set of circumstances, when it's a plain wall with a constant thermal conductivity, no generation, and temperature varying only in one dimension, the solution at steady state looks like this. So the temperature at any point x is equal to surface temperature 1 plus the difference in surface temperatures times x over L. So just to make this a little bit more clear, I want to walk through how exactly we get that form of the equation. So we're going to start here, and I'll just pull up a white screen. So we had our generic temperature profile look like this. The temperature is equal to a constant times x plus another constant. Just a very simple equation, a basic line with a slope and an intercept. So we're going to apply those boundary conditions. So we had at x is equal to 0, we had our temperature is equal to surface temperature 1. So what you can do here is some very simple substitution, and we just substitute 0 in here, and then we solve that equation. So we end up with, you also substitute surface temperature in here. So the temperature is equal to the surface temperature 1. That equals 0 plus C2. So pretty simple. We've solved for C2 now. So we now know that C2 is just equal to TS1. Now we can substitute our next boundary condition at x is equal to L. Now we get T is equal to TS2, and we're going to substitute that in. So now TS2 is equal to C1 times x, and instead of using x, we're actually going to plug in L here, because x is equal to L under these conditions. So C1 times L plus C2 goes here, but we already know that C2 is equal to surface temperature 1. Alright, and now we can solve for C1. And we know C1 is equal to TS2 minus TS1 divided by L. So now if we were to take these two constants of integration, which we now know, these are all just constant terms, things that are known and that don't change in the problem. We substitute those back into our generic equation, and we get the temperature as a function of x is equal to C1. So I'm going to substitute in our C1 here. So that is TS2 minus TS1 divided by L. So it's C1 multiplied by x plus C2, which is just TS1. So now we've done this really simple integration. We took an equation that started out looking pretty complex, and using these simplifying assumptions, it actually turns out to be pretty mild. So we go from solving the heat equation, doing two integrations, and getting a temperature distribution. So by solving that equation, we now know how temperature is going to vary through the wall. And the solution always looks like this for these particular circumstances. So a plain wall, temperature varying in one direction, constant thermal conductivity, and no generation, and again, looking at steady state. Alright, now we're going to talk about something called thermal resistance. So thermal resistance can be a really convenient way of solving problems that might have heat transfer through multiple media in series or in parallel. So I'm just going to define some thermal resistances here. So thermal resistance is the ratio of a driving potential to the corresponding transfer rate. So in the class previously, we've talked about these driving forces. For conduction, the driving force is typically a temperature gradient. It is a temperature gradient. For convection, the driving force is just a simple difference in temperature between a surface and a bulk fluid. And for radiation, the driving force is temperature to the fourth power of one surface minus temperature to the fourth power to its surroundings or to another surface. So we're always dealing with these driving forces. So the thermal resistance is defined. It's really just an algebraic tool to help you solve problems a little bit better. But for conduction, so the thermal resistance for conduction is defined as the difference between two temperatures. So going back to the plane wall example, where we had the surface temperatures on each side of the wall. So it's the difference between those two temperatures divided by the actual flow of heat between the two. So from this, so we know we've already talked about how do you define Q by conduction, and it looks like this. So Q conduction is equal to minus K times an area times dt dx. But for that plane wall at steady state with no generation, it actually looks like this. This is the integrated version. K times A over L times TS1 minus TS2. So we have this way of defining conductive flux through a plane wall at steady state with constant thermal conductivity and no generation. So that's the heat flow, and it looks like this. So you can easily back solve and find out that the conductive thermal resistance is just equal to the inverse of this term. So it's L over conductivity times area. And this makes sense. If you've taken a circuits class before, you know that electrical resistance, the higher electrical resistance you have, the harder it is for current to flow through. And it's the same way in heat transfer. The higher the resistance is to heat transfer, the less heat will flow through. So a smaller thermal conductivity makes the conductive resistance bigger. A longer distance between two temperatures, there's more stuff, more material for the heat to have to propagate through. That makes the thermal resistance higher, and that makes the heat transfer through it lower. There's a similar term for convection. So we know that Q for convection is simply defined by Newton's law of cooling, where we have a heat transfer coefficient times the appropriate surface area times Ts1 minus T infinity 1. And so again, we can just back solve and we can find out what the convective thermal resistance is. And it is 1 over H times A. So the bigger the area, or the larger the heat transfer coefficient, we're going to be convecting more heat from the surface to the air, which means we're going to have a smaller convective thermal resistance. So this is just a simple introduction. We'll get more into how you use these thermal resistances, and that's probably when they'll start to make sense, is when you actually start applying them. So for steady state problems, and only for steady state problems, these thermal resistances can come in really handy when you're trying to solve problems. So thermal resistances have different forms. So here, just for reference, we're showing the temperature profile. Sorry, we're defining heat flux and heat rate when you have a plane wall at steady state with no generation and with a constant thermal conductivity. The heat flux can just be defined by taking a delta of the temperatures divided by L, because the temperature profile, if you'll is going to be just a straight line as we solved before. So you're just trying to get the slope of that line. So this ends up being, the derivative of this line ends up being equal through the whole wall. So in these conditions, the math gets even simpler. You just need this very simple algebraic equation to find flux or heat rate through a plane wall. So the thermal resistances come in handy because now you can take the total delta T and you can take the total delta T, divide it by the total resistance, and you can get the flux, or vice versa. This equation is the inverse of that. So you can apply this circuit-like analysis, and the rules are very similar for electric circuits. So let's say we have a plane wall with T1 over here and T2 over here, and this is an air temperature now. And then we have the solid wall in between. Well, if we want to find out the flux from this part of this room to this room, this basically heat has to travel through these three different media. It's going to encounter three different thermal resistances. So that heat has to convect from here to the wall's surface, then it has to conduct through the wall, and then it has to convect back out from this wall surface back out into the air in room 2. So the way to solve for heat flux there is to add up all the thermal resistances. So it's going to encounter a thermal resistance here in room 1 as it convects to the surface of the wall, another thermal resistance as it conducts through this wall, and another thermal resistance as it convects back out into the air. So if we only know these temperatures, and let's say we don't know anything about the surface temperatures here, well, we can find the total thermal conductivity by just doing a simple addition of all the thermal resistances, and we get the total heat transfer through the wall by taking the absolute temperature difference from each end of our system and dividing that by the total thermal resistance. So thermal resistance, we try to be versatile here in the way it's defined. So you can also define thermal resistance per unit surface area, where the per unit surface area term just doesn't have, and it's actually not per unit surface area, it's for unit surface area. So this is the thermal resistance for radiation, and you see it has the area divided. Well, if you just multiply the whole thing through by area, now you're talking about thermal resistance for a unit surface area. So they're just interchangeable terms depending on whether you have information about the cross-sectional area that's appropriate for heat transfer. So for the thermal resistance per unit surface area for conduction is just L over K. So you notice you don't have the cross-sectional area in there. And for convection, it's just 1 over H. And for radiation, you have to, we covered this in a previous lecture, you have to solve for this radiative heat transfer coefficient, which is just a sneaky mathematical way of trying to make radiation look like a linear process, but it's really not. However, it can come in handy, and this is really the only instance where it comes in handy is when you're doing this, using it to calculate thermal resistance. So that same basic definition applies. We use this algebra where we factored out the Stefan Boltzmann law into to get out a raw temperature difference from it. And we've made an algebraic form of this radiative heat transfer coefficient, so it looks a lot like convection. And because using this form makes radiation look like convection, the thermal resistance for a unit surface area looks similar as well. So finally, another type of thermal resistance that can come in handy is what's called a contact resistance. So if you have two different materials that are adjacent to each other and might be touching in some parts and might have some holes in some parts, it can become convenient to define what's called a contact resistance. And there's really a whole lot going on here microscopically, but you can do experiments or you can find thermal properties of interfaces and you can define what's known as a contact resistance. So that's when there's not perfect contact between two different media, so there's not going to be really great heat transfer, and one way to characterize that is to just say, well, these two surfaces have a contact resistance and that would you'd basically just get that number as a constant from somewhere. You don't need a thermal conductivity, you don't need a convection coefficient. You just either experimentally determine that number or find it in a table somewhere. So in some cases there can be, when you have negligible contact resistance, meaning that you have solid materials that are in very firm contact with each other, um, you can have instances where you have heat that's going through multiple, more than two, more than three. In this case, there are 5 different thermal resistances that the heat must travel to get from one room to the other. So it's going to have a thermal resistance of convection going from room 1 to the surface here. Then it's got to conduct through here, through wall A, conduct through wall B, conduct through wall C, and then it has to convect into this other room on the right hand side. So the problem really doesn't get that much harder. It is just a summation of all the thermal resistances, and then to get the total flux, you would just take the two absolute temperature differences and divide that by the total resistance, and that will give you the flux through the wall. So another way of expressing this would be by defining something called the overall heat transfer coefficient. So it's just another form, and sometimes this is preferable to doing the thermal resistances, but the total resistance is just 1 over the overall heat transfer coefficient times area. And you can characterize flux by flux or absolute energy here by saying U. It looks a lot like a convection heat transfer coefficient, but actually in this case it covers the expanse of convection, conduction, 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 and convection. So it's just a more convenient way of lumping all of those different resistances together into something that looks like Newton's law of cooling. So this is a modified form of Newton's law of cooling. All right, before we end this lecture, let's do some interactive questions. So we're going to be looking at that same system. So you have a hot fluid on the left-hand side, you have a cold fluid on the right-hand side, and let's look at question number 1. And we're actually given the temperature profile. So you have convection here and conduction through each of these walls, and then convection on that right side. So just looking at the walls themselves, so wall A, B, and C, which wall section has the lowest conductivity? This is question 1. So as a hint here, you want to be looking at the slopes of those lines. Which section has the lowest conductivity, thermal conductivity? So that is section B. So B, even though we aren't given any information about the thermal conductivity here, we know that section B, if this is at steady state, we know that section B has the lowest conductivity because that lowest conductivity corresponds to the highest slope here. So one way of thinking about this is a material that's not easily conductive. You're going to see large temperature gradients because it's really hard for the heat to penetrate through that surface. So the temperature drops quite quickly, and you can see this if you put your hand on one side of an insulating material and you expect, let's say, you're standing outside of a freezer. If you put your hand on the outside of the freezer, it might feel a lot closer to room temperature, whereas if you're on the inside of the freezer, it's going to feel freezing. So there's going to be a very large, a very steep temperature gradient through that freezer wall, and that's because it's an insulating material with a very low thermal conductivity. So question 2, for the cross-sections shown, which section has the highest thermal resistance? And this could be any section now. It could be the convection or one of the conduction sections. So it's a little bit trickier to tell, but it's basically here. You see the biggest temperature drop on convection here. So this is going to be the room on the right. So has the highest thermal resistance because that highest thermal resistance corresponds to the biggest absolute temperature drop. So again, wall section B here might be a pretty good answer. It just looks like this temperature drop is a little bit more substantial than this overall temperature drop. All right, and question C, for the whole cross section shown, so for the whole system, which part of this system has the highest heat flux? So heat is going to be flowing in this direction, and at what point is the flux the highest? So the answer, this is actually a trick question. The flux will be constant through the whole thing. So heat will be going all the way through. So this can be a really nice tool if you know that, let's say you know these two temperatures and you know the two temperatures of the room air and you know the thermal conductivities of each of these materials. You can actually use that fact, so you can get flux Qx is equal to T infinity 1 minus T infinity 2 divided by the total thermal resistance, and I'm going to use the one that's for unit area because we don't necessarily know anything about the width and height of this wall. And we can say that that's also equal to that's also going to be equal to T infinity 1 minus Ts1, so this temperature, divided by the thermal resistance of convection here, and so let's just call that H1. So you can actually use this, set these equal to each other, and you could use that to solve for something that you might not know before, something like Ts1. So you could use this fact. You'd have to know something about the heat transfer coefficient, but you would already know that in order to solve for this guy. So you can use these relationships to create multiple algebraic equations. So you could also set this equal to Ts1 minus Ts2 divided by the conductive thermal resistance. Let's call that Rcond1. And that's the one for unit surface area. So once you found surface temperature 1, now you could go and use this to find surface temperature 2. So you can actually generate multiple equations here and use those equations to solve for intermediate surface temperatures. So this is a fact that could come in handy when you're doing heat transfer analysis for a plane wall at steady state. Use this thermal resistance method to get flux for an overall system, but because you know flux is equal going through, it's independent of x, then you can create these extra relationships and solve for intermediate surface temperatures. All right, so here's another interactive problem. So you can just do this on your own. So for the plane wall shown, what is the overall thermal resistance for unit surface area? So the way to solve for this would just be to take all the different thermal resistances and add them up. So we're looking for the total thermal resistance for unit area, and that's, so you can see heat has to convect through here. This is the system that, pretty much the system we were just looking at. Heat has to convect here, then it has to conduct through wall A, then wall B, then wall C, and then it has to convect back out into the room on the other side. So this would be 1 over H1, getting that first convective thermal resistance, plus LA divided by KA plus LB divided by KB plus LC divided by KC plus 1 over H2. So if I did this correctly, I get 0.351 meter squared Kelvin per watt.